All right, so we're moving on to 6.2, volumes of solids using discs or washers. Let's take a look at a solid. Imagine that we are rotating it with respect to this axis. When we are rotating with respect to a horizontal axis, imagine that this is a loaf of bread and we are cutting it in small slices. Well, if we're cutting it in small slices, just imagine this is the width of each slice. And since there is no empty or hollow center, we're going to use the method of disc or discs, in which this is our famous dx, or also delta x, the same thing. And this is the area. Notice that the area of the disk changes from leftmost point till the rightmost point. It's not exactly the same. So in this particular case, rotating this area around the horizontal axis, we will determine the volume of a solid. Obviously, we have to determine the area of the disk. So the area of a disk is pi radius squared, and multiplied, of course, by the width of the disk. So this disk has the following volume: pi r squared, where r is the radius of the disk, multiplied by dx. So then the volume will be the integral from a to b, from pi, the radius squared, of course, multiplied by dx. Since we sweep the entire volume with tiny disks from left to right, from A to B, this will be the entire volume of the solid, rotating it with respect to a horizontal axis, which means, again, imagine that we are cutting it in small slices from left to right. Okay, what happens if the scenario now is in this way, and this is the axis, and we are rotating it with respect to a vertical axis from A to B. So in this case, the rotation will enable us to cut it in small disks from the smallest A, for the smallest value, till the upper value for B. But this time we are going to integrate with respect to y. So the volume, of course, we have the same picture, the same width, but this time it's the dy, or of course dy, delta y, the same thing. So the volume of this solid will be, of course, the integral from a to b, pi, the radius. What radius? This is the radius. Okay, so the radius squared, but this time times dy. And now what happens, we're going to look at examples in a minute, but what happens if we have, let's say, something like this. We're going to look at it in a moment. And we are rotating it with respect to a horizontal axis. Okay, so for a particular x value, we're always going to picture this rectangle that sweeps the area from left to right, of course, from A to B. But this time we have a hollow center. So the method will be a washer, or the washer method, okay? Because we are going to have to remove the inside, which is hollow in this case. Okay, so let's look at a few examples and see how we illustrate what we just discussed about volumes of solids, obtained by rotating an area around a particular axis. Of course, the axis doesn't have to be in the middle. It could also be on the outside or a different position. Okay, so we're going to look at a few examples in a minute. Okay, so just to make sure that you understand that this can be determined with a limit of the Riemann sum in the same way. So this is the limit as n subintervals from a to b, from the sum from I equals, of course, 1 through the last one, from the area of xi, of course, times dx. Exactly the same thing as we did with areas between curves or among curves. So let's look at a few examples. Let's start with 13 on page 456. They are giving us y equals the square root of x minus 1. They're giving us y equals 0, x equals 5, and they say make sure that you are rotating it about the x-axis. Okay, so like before, we have to graph, we have to find points of intersection if we need to, and then we have to decide whether we integrate with respect to x or with respect to y. If we are rotating about the x-axis, it means that we are rotating about a horizontal axis. So we will be integrating with respect to x from the leftmost point till the rightmost point. So the moment we have about the x-axis, we know we integrate with respect to x. Good. So let's take a look at the picture. Let's see if I can fit it in here. For such a function, it's a square root. X minus 1, by definition of the square root, has to be a number greater than or equal to 0. Obviously, this means greater than or equal to 1. So the domain of this function starts at 1 and goes to infinity. So this is y equals the square root of x minus 1. So this is accounted for. Next one, y equals 0. Very easy, is the x-axis. Done. The next one, x equals 5. So if this is 1, 2, 3, 4, here is x equals 5. And now I have the area enclosed by these curves. We're asked to rotate it about the x-axis. Okay, fine. So I'm going to rotate it with respect to the x-axis, and it will look something like this. Since we are rotating with respect to the x-axis, I will say this. For a particular x value, I will picture the disk. Why is it a disk and not a washer? Because there is no hollow center. So I'm going to use a disk. I will determine or show any particular rectangle. For this particular x, the radius of this piece is this height. Radius. Why is this important? So first of all, the volume will be pi. I can leave the pi outside. Of course, the integral between 1 and 5 from the radius squared times dx. In my big example here, of course, this is the dx. Okay, now what is the radius? It's this height. What is this height? Is the y value for this x value, which is this. So the distance between this, where the function and the vertical x value, if you want, they meet at this point, the height is the y value, which is, and I have to square it. So It's the square root of x minus 1 squared. Pi, the integral from 1 to 5, from x minus 1 dx. After you square, because it's pi, r squared times dx. Moving on. Let's continue. So therefore, pi x squared over 2 minus x from 1 to 5. We plug in 5, 25 over 2, minus, careful now, when I plug in 1, minus 1/2, I plug in 1 is negative already, plus 1. So then pi, 25 halves minus 1/2 is 24 over 2, which is 12. And negative 5 plus 1 is negative 4. So this is 8 pi, whatever units cubed, because it's a volume. Okay, moving on to another example. Let's say 15 on the same page, 456. Let's take a look. And we are given x equals to the square root of y. We are given x equals 0, y equals 9. Careful now, about the y-axis. Knowing that we are rotating about the y-axis, in any direction, it doesn't matter, we know that we are going to integrate with respect to y, slicing the bread, if you want, the loaf of bread, from the bottom to the top. So we're going to graph first. Okay, so let's start with x equals 0. Here it is. Done. Y equals 9. 3, 3, 3. So 6 and 3, and here is y equals 9. Okay, and I don't ever want to forget to label the axis. So let's do that from the beginning. Y equals 9 is done. And now I want to graph this. I want to graph x equals to the square root of y. I'm going to square both sides. X squared equals 4y, which means y equals x squared over 4. So this is a parabola. I know that it has the vertex at 0, 0. And I know how to graph it, but I would like to know exactly where it crosses y equals 9. I need those points of intersection. Points of intersection. Okay, so I'm going to set y equal to 9. I'm going to cross multiply. I get x squared equals 36. I'll take square roots. X equals plus or minus 6. Okay, 1, 2. I mean 3, I meant to say, and 3, 3. So negative, negative. So here are the points of intersection. Here is the graph. Of x equals to the square root of y. Okay, where is the area enclosed by x, which is to the square root of y, x equals 0, and y equals 9, right here. We are going to rotate it with respect to the y-axis. Now we are going to say this. Remember here we said for a particular x, we were integrating with respect to x. For a particular x, this time we are going to say for a particular y value, I'm going to picture the disk. Of course, it's all the way. So what is the radius? The radius of the disk is this. But what is this radius? How much is it? Well, it's the x value. But what does the x value represent? to the square root of y. I know I have to integrate with respect to y. So then the volume in this case will be pi, from 0 to 9, from the radius squared. X is the radius. X is this height. But x is to the square root of y. To the square root of y, everything squared, times dy. So therefore we have pi, the integral from 0 to 9 from 4y dy, which is 4 pi y squared over 2 from 0 to 9. So I'll simplify and I have 2 pi times 9 squared, which is 81, 162 pi, of course, units cubed. Okay, moving on. Let's look at other examples. Okay, I'm on page 3. Let's take a look at 19. Also on page 456, we have y equals x cubed, y equals the square root of x, and it says about the x-axis. So when we rotate with respect to a horizontal axis, we integrate with respect to x. Okay, so let's take a look at how this looks like and find the area that we are rotating. So here's x cubed, famous x cubed, y equals x cubed, and then y equals the square root of x. I know for sure. Then I have to state this. Okay, x can not be a negative number. We're going to graph y equals the square root of x, and we realize that this is the area in question. It says about the x-axis, fine. I'm going to picture the area on the other side. And here it is. We need to find the point of intersection, so we can integrate between 0 and this point with respect to the x-axis, with respect to x. Okay, I will set this equal to each other. So x cubed equals the square root of x. We square both sides. X to the 6th equals x. X to the 6th minus x equals 0. X to the 5th minus 1 equals 0. There are obviously 6 solutions, but there are only x equals 0 and x equals 1 that are of interest to us. The negative side has no meaning because x has to be greater than or equal to 0. Okay, so then this is 1. So the volume then will be, of course, pi can stay outside. We are integrating with respect to x between 0 and 1. So then we are going to say, since we are integrated with respect to x, we're going to say this. For a particular x value, we are going to picture, in this particular case, it will be a washer. This is one radius. I'm going to call it R1. And here is the other radius. I'm going to call it R2. So therefore, R1 minus R2, of course, R1 squared minus R2 squared. So in parentheses, R1. What is R1 for this particular x value? Well, it lies on the square root of x. So it would be the square root of x, everything squared, minus R2. Well, R2 lies on x cubed. So it will be x cubed, everything squared, and of course, dx. Good. From this moment on, we have pi, the integral from 0 to 1, from x minus x to the 6th dx, which is pi x squared over 2 minus x to the 7th over 7 from 0 to 1, luckily only from 0 to 1. So pi 1/2 minus 1/7, 7 minus 2, so 5 pi over 14. Okay, I think we should look at one more.